Hey, welcome back. Today in Short Text 331, we are going to be talking about orthogonal functions and special polynomials. So let's say we have a basis such as this one for our vector space, and we're going to be actually focusing on this basis for the whole of this video. So this basis is made out of monomials, 1x, x squared, and so on. And of course, we know these are linearly independent. There is no way to form a linear combination of some of them and get one of the other ones. So we're pretty sure that's linearly independent, and it generates a space, which of course, if we consider monomials all the way to infinite order, then this is going to be an infinite dimensional vector space. It doesn't have to be for the purposes of this video. You can imagine that it's finite dimensional if you want. So there could be a maximum power here if that is your preference. And the point we want to make here is that we can orthogonalize them and optionally also normalize them after we orthogonalize them using the Gram-Schmidt process that we discussed in a previous video. So we're going to be then applying the Gram-Schmidt process to this basis of monomials. And for that purpose, we will need in our space of functions a well-defined inner product. Okay, and we can do that in a variety of ways. We could define the inner product as in A here. Then the inner product between f and g is the integral between -1 and 1 of the product of the functions, that's a possibility. We may define it as in B here with an integral from -infinity to infinity, the product of the functions and the Gaussian factor to ensure convergence in both plus and minus infinity. Or perhaps we could do an integral from 0 to infinity and use e to the minus x as a regulating factor so that the integral converges for sure at infinity. And so on and so forth. There's a variety of weight functions that we could use as long as they're positive, then and they help us with convergence, then we're fine. And remember that we want to make sure that this integral converges, and so either the endpoints have to be finite or there has to be some weight factor here to ensure that the product of monomials can be integrated to a finite result, and so we would have a well-defined inner product. So the key point that I want to make here is that this form of the inner product, whichever we choose, will determine which type of polynomials we end up with once we orthogonalize. In other words, the Gram-Schmidt process will take this as an input, coupled with whatever choice of inner product we do, any of these three or some other one, and then out will come another set of polynomials, and the type of polynomials we end up with will depend on what kind of inner product we choose. And so if we choose A, then the Gram-Schmidt process will actually produce the Legendre polynomials. Okay, so if you choose this inner product and you orthogonalize the monomials, you end up with the Legendre polynomials. And if you do that, if you go through that process, which we started in fact in a previous video, and then you normalize the polynomials and you calculate the first few, you will see, if you look up the Legendre polynomials, that those are indeed the polynomials we get. On the other hand, if we choose B with the Gaussian factor, like this, e to the minus x squared, then we will produce the Hermite polynomials. And you can come up with your own inner product and invent your own U polynomials. Okay, there's nothing preventing us from doing here e to the minus x to the fourth, for example. Maybe the integral type result would be difficult, but in principle you could do that and you could see what you get. Now, in a previous video, we did the first three cases of A. Like I said, we obtained the first three Legendre polynomials using this inner product, and now we're going to be doing B. And at this point, I want to say, as always, this series is meant for my students at UNC Chapel Hill. And if you find this series helpful, regardless of whether you're a student or not, please like and subscribe. It would really help the channel. Now, if you're not a student at UNC and you're looking for a tutor in physics or math, either in English or in Spanish, I can help you in both cases. You can contact me at shorttakes331@gmail.com, or you can leave a message in the comment section below. So let's go ahead and let's try. Remember that in the Gram-Schmidt process, we start with vectors we call V. In our case, the vectors are V1 is 1, V2 is x, V3 is x squared, and so on and so forth. And like I said, in the case B, we're going to be taking the inner product to be the integral from -infinity to infinity, f of x, g of x, e to the minus x squared. In the Gram-Schmidt process, if you remember, the first output vector is simply the same as the first input vector. And then when we go to the second output vector, what we have to do is subtract the projection okay, of v2 onto v1, onto w1. And so w2 is v2 minus that projection times w1 divided by this magnitude squared of w1 of w1. So you calculate this w1 with itself. And if you do that calculation, you say, well, okay, v2 is x, as we see here. Then we have to take the inner product of v2, which is x, with w1, which is just 1. And then we have to divide by the inner product of w1 with w1, which is this other integral down here, times 1. The 1 is simply this w1 here. So I'm writing explicitly all the terms here. So what this comes to over here is the top is the integral from minus infinity to infinity of x times 1 times e to the minus x squared. So that's just x e to the minus x squared. On the bottom, we have the integral of e to the minus x squared dx. But it turns out that this top integral is 0. And why is that? Well, we have the product here of an odd function. So x takes positive values and mirrored negative values on the negative axis. And here you have an even function, a function that takes on the positive and negative sides of the real axis the same values, just mirrored. And so when you have that integral, you will have as many positive contributions to this integral as negative contributions with the same magnitude but different sign. In other words, the area under the curve of this function is just 0. Okay, there will be parts above the real axis, part below the real axis, and it will all add together to 0. It will be a vanishing contribution. So we don't even need to worry about the bottom integral here. The top is just 0. And actually, no, we know that the bottom one is non-zero, but it doesn't matter. So the top is 0, all this vanishes, and so our result for W2 is simply x, and that's where the calculation ends. All right, so far so good. W1 is 1, W2 is x. What about W3? Well, the formula for W3 that we saw last time we talked about Gram-Schmidt, is that W3 is V3 minus this inner product divided by the inner product W1 with itself times W1, and similarly minus V3 with W2, W2 with W2, all times W2. So now we have a list of integrals we need to calculate. So let's see. Well, we need to calculate V3 with W1. That's going to give us some non-trivial result. X squared is positive. This quantity is positive as well, except at the origin where this is 0, but otherwise it's a positive contribution, so this will be non-zero, a non-zero integral. All right, we need to calculate that. What about V3 with W2? Well, V3 with W2 needs to be calculated. And so we say, okay, well, V3 is simply x squared, and W2 is simply x, so we get an x cubed. Okay, we get an x squared from this, and x from this, and this x cubed times e to the minus x squared. So again, we have an odd function and an even function, a function that takes positive values on the positive real axis, negative values on the negative real axis, mirrored around the origin. And this was an even function. It takes positive values on both sides, against mirrored around x equals 0. And so the contributions to this integral are just all 0. They all cancel each other out. And so this is 0. Oh, this is great. So then we don't need to worry about this term at all. Okay, there's an x, there's a W2 here, which will give us an x. There's something here which is non-vanishing, but this top coefficient is 0. So this term completely goes away, and we only need to worry about this term. Okay, we know that W1 is 1. We know that this integral is some value that is finite that we have to calculate. And then the top is also something that we have to calculate. And so let's see. So then we're going to need then a couple of integrals. We're going to need an integral that in general takes this form. I'm going to call it I sub n, as the integral from minus infinity to infinity, x to the 2n, e to the minus x squared dx. And here we're interested in n equals 0 for the bottom part, and n equals 1 for the top part, which is this integral here. So we really need to calculate two integrals, but we'll see that there's a technique that allows us to calculate all of these for any value of n, which in principle are needed for future w's. Okay, so here we're going up to w3, but if we want to go to w4, w5, and so on, then we're going to need more and more complicated versions of this, or rather higher and higher powers n here in this integral. And you can see already, by the way, that I'm focusing on the even results here, the even powers, because the odd powers will always have this problem or this property that tells us that the result vanishes. So if I were to insert here instead of 2n plus 1 to account for the odd powers, then those will simply vanish. And so I can focus on the even powers. Now, we know, and I'm going to say we know, but we'll discuss it in a future lecture, in a future video, that the zeroth order integral as a function of lambda, where I've inserted lambda here in the exponent, is the result that is known. So the integral from minus infinity to infinity of e to the minus lambda x squared dx is simply square root of pi over lambda. This is the result that is known. We'll assume that is known. We'll prove it in a future video. But for now, we'll take it as something that is known. And that allows us to use a trick that is often attributed to Feynman, although I suspect that other people also had discovered that before and after Feynman popularized it. That is that we can take a derivative with respect to this parameter lambda. It has nothing to do with x, by the way. This is just a parameter that we inserted there by hand. But since we know the result as a function of lambda, we can take a derivative on both sides of the equation. So how does that help us? Well, on the left side of the equation, if we take a derivative with respect to lambda, we will see that an x squared comes down. And this is kind of what we need here. And on the right-hand side of the equation, if we take a derivative of lambda, it's something we can calculate. And so we will be doing operations on both sides to get the calculation, to get the result that we need. So let's see how that works. In particular, if you take just one derivative, you get I1, but if you take higher derivatives, you can get I2, I3, and so on, an arbitrary n. So again, let's see how that works out. So if I take I0, this function I define here, and I take a derivative with respect to lambda, then the derivative goes right through the integral. And if you don't feel comfortable about this, keep in mind that this integral has no problems whatsoever. It's absolutely a convergent integral, has no issues, neither at infinity or minus infinity, nowhere in between. This function is a really nice function. It's infinitely differentiable. It has no issues at all. And so you can go ahead and take that derivative without any problems and any qualms. And so you go ahead and you do that. And when you do, from the exponent, remember we're taking the derivative with respect to lambda, okay, not x. X is an integrated variable, so we cannot touch x, but we touch lambda, and down comes a minus x squared. And then we're very close to the integral that we need. Remember, we need this integral here. So up to a minus sign, we have that integral. And if we were to take more derivatives, you can see that we would access any arbitrary power to n here in the exponent. And so we go ahead then and we say, if we flip the sign on both sides of the equation, then minus the derivative with respect to lambda of I0 of lambda gives us simply I1, which is one of the integrals that we need, the main one that we need today to get to calculate W3. Okay. By the way, we also need the bottom here part of the integral of this expression, W1, and that is simply setting lambda equal to 1 here, and that would get us just square root of pi. So you can convince yourself that that's true. It's very easy, corresponds to n equals 0 here. So it's just setting lambda to 1, and we'll have that answer for the bottom part of that ratio. And so, so far so good. And so we also know that, so this is a part of how you solve for I1. So this simply tells us if you take a derivative of lambda and you flip the sign, you get I1. Okay, but how do you actually calculate I1? Well, when you take the other side of the equation that we saw up here, we know the result for this integral. We don't just know the form of the integral that allows us to identify that I0 has some relationship to I1 and I2 and so on, but we also know the result. So by knowing the result, you can explicitly take that derivative as well. So in other words, this on the left-hand side here is actually something we can calculate. So we go ahead and we do that. And when we do that, we get minus the square root of pi times minus 1/2 lambda to the minus 3/2. And now we're going to have to take lambda equal to 1 in this expression. And when you do, you find that I1, yeah, which remember we identify I1 with this when you set lambda equal to 1, you get square root of pi over 2. In other words, we get that I0 evaluated at 1 is square root of pi, and I1 is square root of pi over 2. And those are the two integrals that we need. Let me go back to the top up here. So we needed to calculate W3, we need two terms, this term and this term. We established that this term just vanishes because this integral is 0. So we don't worry about this term. Now we go into this term and we have the top part, the numerator and the denominator. The numerator is what we calculate using Feynman's trick. The denominator, I haven't told you exactly how we calculate this integral, but it's contained in this integral. Okay, this bottom part is simply the integral of e to the minus x squared. So we get it from setting lambda equal to 1 here, and so that's square root of pi. So this bottom is just square root of pi. And the top, according to the Feynman trick, comes from simply taking a derivative of this expression and setting lambda equal to 1 at the end. And when we do that, going through these steps, here we get square root of pi over 2. And so in other words, what's going to happen is that this ratio here is square root of pi over 2 and divided by square root of pi. So the whole thing is just 1/2. Okay, so that's all there is. So all this work just for 1/2. So we will clarify that below. I want to say here that I want to emphasize that if you take more derivatives, you can access higher powers of n, and so you can access any i's of n. Okay, so this Feynman trick is very powerful. If you take this function and you take arbitrary derivatives with respect to lambda, you can access all the in's here that you want and that you will ever need. Now, also interesting is that you can evaluate at different values of lambda, and that in that way you also get other integrals for free. For example, if you want the integral of minus infinity to infinity of x squared e to the minus 2x squared, you do the same calculation we did, but instead of setting lambda equal to 1 at the end here, you set lambda equal to 2. And that will give you the result for that. And that's nice. Okay, it's kind of a relatively easy thing to see. And you may not need a trick to that calculation, but it's nice to know that you have access to that as well. So knowing these Gaussian integrals is actually not something that's just useful for generating these orthogonal polynomials. The reason I'm emphasizing these Gaussian integrals and how to do them is that actually it's essential in physics. So modern physics, modern theoretical physics in particular, uses the tools of quantum field theory, and these types of integrals, these Gaussian integrals, are everywhere in quantum field theory. And so if you know these integrals really well, then it will help you in your theoretical physics career, if that's the direction you're going. So now going back to our W3, let's reassemble our results. We said W3 is V3, which is x squared minus this contribution. Remember, the other one vanishes. And now, so we have x squared minus square root of pi divided by 2 divided by square root of pi, which is this guy down here. And so it's just x squared minus 1/2. And that's all there is. Now we can normalize this guy. We could calculate the normalization of W3 with itself and divide by the square root of that. We could do that here. I haven't done it, but that's basically the Hermite polynomial. That's the content of the polynomial. So these are very important functions, in fact, these Hermite polynomials, because they characterize the quantum harmonic oscillator. When you study the quantum harmonic oscillator, you will see that the wave functions, okay, the functions that characterize the eigenstates of the Hamiltonian, so the stable states of the system, are some constants. Then there's a Gaussian, a little bit different from what we saw. It's e to minus x squared divided by 2. The whole exponent is divided by 2. And some Hermite polynomial of some degree, which could be 1, 2, 3, 4, and so on, depending on which quantum state you're interested in, of some constant times x. So these Hermite polynomials are an essential part of these eigenstates of the harmonic oscillator. There's another case that you could play with if you want. It's called the Jacobi polynomials, where again you try to orthonormalize your monomials. So we use the same basis of monomials, 1, x, x squared, and so on, as high as you want to go. But now we define the inner product in a different way. We define the inner product of f with g as the integral from -1 to 1 of 1 minus x to the power alpha times 1 plus x to the power beta times the product of f with g dx. And here, this is defined for alpha and beta greater than -1 to make sure there are no issues with convergence in any way. And that's it. That's all I have for you. As I said before, this series is meant for my students at UNC. Whether you're a student at UNC or not, if you find this series helpful, please consider liking this video and subscribing to the channel. If you're not a UNC student and need help for physics or math in English or in Spanish, then you can contact me at shorttext331@gmail.com, or you can leave a message in the comment section below and I'll be happy to contact you and we'll take it from there. That's all for today. I hope you enjoyed this video and I'll see you next time.